After graduating from NIT JCR in 1998, he worked for 2.5 years in Tata Steel Jamshedpur. Then he left for postgraduate studies and obtained a PhD from Arizona State University. He also worked as a postdoctoral fellow at the Center of Advanced Power, Florida State University, USA. He has been with Department of Electrical Engineering, IIT Delhi, since 2007. Now he's a power grid chair professor at IIT Delhi. He has supervised more than 10 PhDs. He has received different awards in his professional field. He is a senior member of IEEE USA, and he is a society member of IEEE Power Engineering Society. So he has completed more than 10 number of sponsored research project as a PI and co-PI. So with these few words, I would request Professor Shen to share his screen and start his presentation. Thank you, sir.
Okay. Thank you very much, Dr. Bhaumik, for inviting me to this presentation, to make the presentation on a topic that is of extreme relevance in today's power system operation and control. So, first question is, am I audible and am I visible?
Yes, you're audible, sir.
Oh, all right. And so, okay, let me try to. So, I'm trying to share my
Yes, sir.
screen.
Right now we can start. Sir, right now we can start.
Okay, all right, good. Yeah, is it visible, my screen?
No, sir. Yes, no.
Is it visible now? Is my screen visible now?
No, sir. Sir, select window first.
Okay. Maybe what
You
I
can
will
share
do
your
is...
window or you can share your desktop.
Yeah, that's what I'm trying to do, sharing my window. I don't know what is wrong here. I seem to be doing what I usually do. You cannot see my slides?
No, sir.
Okay. Can you see my slides now?
Yes, it's okay right now.
Okay.
It's fine, sir.
Is it visible in the screen in the?
Yes, sir. Is it visible now?
Okay.
It is
Okay.
visible.
All right. Thank you. So, welcome to this program on this. Welcome to the lecture. Thank you for inviting me to deliver the lecture online. So, in this in the middle of this pandemic, I think this is the best we can do to keep in touch with each other, our peer group. Normally, these kind of lectures are also associated with some interactions, but I hope and I don't know how much interaction we will be able to do over this online Microsoft Teams platform. So if in the middle of this presentation anybody has any question, I would be very grateful if you will stop me and we can discuss. So because I don't know what is the level of understanding of the current audience regarding the issues that I'm going to talk about. So I expect that at least everybody is an electrical engineer. But even if you're not an electrical engineer, at least if you're an engineer, that is enough to understand most of the things that I'm going to talk about today. However, it will be nice if somebody can share their experience or or make a comment on the various issues that we are talking about here. That will make the discussions and the presentation and this whole session more lively and exciting for everybody. So I'm going to talk about the renewable energy. And so renewable energy, you know that it is the energy that is um, renewable. So basically it comes from the wind, solar, biogas and things like that. So traditionally the electricity was being generated using non-renewable sources, like for instance thermal and thermal and hydro. Hydro, although some countries define it as a renewable source, but in India we define only small hydro as renewable. Large hydro, like reservoir-based hydro, that it is not renewable energy source. So what is the energy future? Let me start with this slide, which is a little bit depressing slide. The energy future of our country and what is the need to go for renewable energy. So the first thing that you see on the left is the table which shows the total primary energy supply that is available per capita. And the different classes that are installed are shown are for the world. The number is, well, this is actually 2012 data. So it's about 6.5 billion is the population here. Then for Asia it is 2.2 billion, for Africa it is 1 billion, and China 1.3, and for India it is 1.1 billion. The second column talks about the total primary energy supply that is represented in terms of tons of oil equivalent. So this is like, you know, firewood, starting from firewood, cooking gas, and everything that is available. Okay, it is not just electricity. Electricity is referred to in the third column, which is the amount of number of units per capita, and these are all yearly, annual numbers. So if you look at the total energy, the second column, then the number for Africa is 0.67, for China it is 1.7, and for India it is 0.58. So once again the unit is tons of oil equivalent. So you can see that India, the amount of primary energy supply per capita is lower than Africa. Similarly, if you look at the number of units that a typical person in India spends over a year, then the number for India is 597. For China, it is 2,600. For Africa, it is 561. And for United States, it is 12,000. So you can see the huge divide between the citizens living in India and, for instance, we are just about marginally over and above a citizen of Africa. So this actually shows, and of course the carbon dioxide emissions, it is very small for our country, 1.37. Although if you, this is per capita, and if you multiply this by the population, then it becomes a very large number. In United States, the carbon dioxide per capita emission is extremely high, 16.9, tremendously high. So the energy supply in India is low. The reason being, we are basically an energy deficient country. And of course, we are a warm country. So some of the countries noted here, for instance, China, United States, OECD, that means the economically developed countries. These countries are actually cold countries. They are not very warm. So they have cold in terms of climate I'm talking about. So they have a lot of heating needs, heating requirements. People cannot survive in those countries without spending a lot of energy. While in our country, it's a warm country, so the amount of energy required for survival is not much. So that is one of the reasons, of course, why our total primary energy supply per capita is lower than the other groups. On the right, you have the summary of the resources that are available in our country, and you can see there's a box made for the fossil fuel resources like coal, lignite, oil, and gas. And the first thing that is striking here is that if you look at the 2007 production rate, then the coal is expected to last about 169 years. But that production rate is increasing at very high speed, and if it continues to increase in that same speed, then the coal is expected to get over within 40 years. This data is of course 2012, and this is actually an article in Power Energy magazine. Then so that means we need to look for nuclear, hydro, and others. So nuclear, we are in the middle of a 3-stage nuclear program, which is very small, which is very slow. It is expected that the nuclear program will mature by about 2030. And if that happens, then we have vast amounts of thorium reserves, and those thorium reserves can be utilized to generate a lot of electricity. There are, of course, societal perceptions regarding nuclear power. People are very scared of nuclear power stations coming up in their backyard. So, of course, we have to factor that in when we look at the expansion of nuclear power. When we look at hydro, we have tremendous amount of hydro potential. But again, hydro that is talked about here is the large hydro potential. And this large hydro potential is subject to building large dams and causing a lot of ecological damage. People are displaced and societies are disrupted, cultures are disrupted. So of course this also comes with a lot of baggage. So the only option to go for is wind and solar. Now wind, we do not have currently the technology to go for offshore wind farms. We are still installing wind farms only on land. Offshore wind farms means wind farms that are installed in the ocean. So offshore wind farms, the benefit of offshore wind farms is that the speed of the wind is slowed by the terrain over which it blows. So if the wind is blowing over a forested area or an area where there are a lot of buildings or there is a lot of trees, grasslands, so depending on the terrain over which the wind is blowing, the wind speed will slow down. So if you want to catch the high wind, you need to build very tall towers. So the onshore, the terrestrial, the land-based wind farms require building of very tall towers, number one. Number two, the blades, the wind turbine blades also have to be very long. So typically about 30-35 meters long, so that they complete a circle of maybe 60 to 90 meters. So this is the only way to generate 3 to 5 to 7 megawatts of power per turbine on the land. But if you go to the oceans, the water has a much lower slowing down effect on the wind. So therefore, you do not have to build very tall towers to catch the high wind. Also, in the ocean, the blowing of the wind is relatively more steady and more predictable. On land, it is not. So the variability of wind on land is high if you move from a location by a few kilometers. But on ocean, the wind remains relatively steady and predictable over large areas. So therefore, wind farms built on offshore have a higher potential. And this potential, unfortunately, has not yet been estimated in India as of 2012. But today there are plans of going for offshore wind farms. So all countries like Europe and Japan and USA who have invested heavily into wind turbine technology have gone for offshore wind farms. Another reason for going for offshore wind farms is land, precious agricultural land is not taken up by the turbines. So the farmers complain that the, the, the presence of the wind turbine creates noise and interferes with their agricultural practices. Also, ecologists suspect that wind turbines sometimes create some problems for the various birds and animals living in that particular geographical location. So these problems are taken care of if you install the wind farms offshore. Solar technology, we have tremendous amount of solar technology. So if you look at the solar, we have, other than the North Indian Gangetic Plain, in the extreme north near Ladakh, we have huge amounts of solar potential, and down south we have tremendous amounts of solar potential. The reason why we do not have sufficient solar potential in the Gangetic Plain is because of pollution and the gases that are emitted by agricultural practices. So there are studies going on at IIT Delhi and other places also all over India which try to measure the impact of aerosols, impact of pollution on the solar potentials in these areas. And those studies have confirmed, for instance, a study in IIT Delhi has confirmed that during lockdown, our solar potential, solar generation actually improved in rooftop systems that have been installed in Delhi. Also, one more thing is that if you just look at pollution, typically the understanding in Delhi is that pollution in winter is more severe compared to the pollution in summer. So winter pollution is more severe because the gases, the aerosols, the particulate matter settles down, and that creates a lot of discomfort to the people living in the cities. In summer, on the other hand, the particulate matter, the gases, they rise because of the hot air, and therefore the effect of pollution is much lower on the people living in the cities. So therefore the perception is that summer pollution in Delhi is much less. In Delhi there's a different kind of problem in summer. We have this problem of dust. So that dust creates a lot of particulate matter in the atmosphere, but that also rises because of the hot winds blowing. However, it needs to be reiterated that even though the particulate matter is rising and therefore not creating so much of discomfort to the people in summer, but the total amount of particulate matter that the sun rays have to deal with before they reach the ground is more or less the same throughout the year. This is very important. As a result, we observe that throughout the year, the pollution from the point of view of solar photovoltaic generation is relatively constant, and our solar generation is significantly hampered because of this pollution. And so the annual estimates of solar generation potential in North India is significantly lower than what it should have been given the geographical location. So we have, nevertheless, we do have a lot of solar potential in India right now, and we are going ahead with installing lots and lots of solar potential. So the idea is, I think by 2023, that means the next couple of years, by the next couple of years, about 175 gigawatts of renewable energy are going to be installed, of which at least 100 gigawatts of solar is going to be installed, and about 75 gigawatts of wind farms are going to be installed. This is a tremendous increase in the solar capacity. So what is the impact of such kind of renewable energy installation on the grid? So we talk about something called grid flexibility. So one of the biggest problems with the integration of renewable energy is the difficulty to maintain load generation balance. Um, the sun does not always shine. So if you have 100 gigawatts of solar integrated into the grid,
Sir, you are not audible, sir.
Am I audible?
Yes, right now it's okay, sir. It's fine, sir.
I think there is some problem. So I'm
Fine,
sitting in
sir.
my office, but I think there is some problem with the IIT network. So from the morning itself, there is the internet is coming and going. So are you able to see my slides right now?
Yes, sir.
Yes, it is okay right now, sir. Flexible
All
enhancement.
right. Okay, great. Thank you. So we talk about the renewable energy curtailment. So the curtailment means that during high so if you have the grid, if you look at our Indian grid, the grid has been developed in order to evacuate power from the locations where it is generated to the location where it is consumed. So power generally was generated in Bihar, Uttar Pradesh, Bengal, Orissa, Madhya Pradesh, Chhattisgarh. So these are the big generation centers of electricity in India, and the consumption maximum was in the western part of India, Gujarat, Maharashtra, Tamil Nadu, and of course the NCR region. So these are the big consumers of electricity in India. So most of the transmission lines were developed in order to fulfill this consumption pattern. Now, the renewable energy generation is coming up in other areas, for instance, Gujarat, for instance, in Rajasthan, for instance, in Andhra Pradesh. Now, here there was no such transmission systems existing. So, as a result, there is a lot of congestion in the transmission lines. And because of these congestions, sometimes the wind farms and the solar farms are asked to ramp down. So this is called renewable energy curtailment. And this is not a good sign. It means that you are actually asking the wind turbine to switch off because the line cannot evacuate the power that is being generated. So this significant renewable energy curtailment is a very big problem. The third problem comes from area balance violations. So for instance, when you have two areas which have a certain contracted power exchange. So for example, area 1 has contracted with area 2 for a power exchange of, let's say, 500 megawatts. Now because of renewable energy violations or renewable energy variations, the wind does not blow, and so instead of transferring 500 megawatts, area 2 is maybe transferring 400 megawatts. So that means there is a violation of the area balance, and these kind of violations are expected to be sustained and very frequent as more and more renewable energy becomes integrated into the grid. Threat to the system integrity and reliability, of course, if you do not have enough generation or if you have excess generation, the loads will be affected, and that is what I mean by reliability. Also, if lines are overloaded, they will trip. If the lines are underloaded, you will have overvoltage condition and they will trip. So the system integrity would be disturbed. So for instance, in Gujarat, a few years ago, a very common problem in the morning was that when the solar would ramp up, all the transmission lines connecting the thermal generators, coal-based generators to the grid, those transmission lines would become underloaded, and as a result would see significant overvoltages. This overvoltage would result in reactive power flowing into the generator rather than the reactive power being drawn out of the generator. So in the morning, the generator would start operating at leading power factor, and this would lead to stability issues and the generators would eventually trip. So this problem was solved to some extent by installing reactors, shunt reactors at the generating stations, which would actually consume reactive power, which would be switched on in the mornings so as to consume reactive power and therefore keep the voltage under control, reduce over voltage. So the way ahead is, of course, to go for flexible resources. Right? These flexible resources are dispatchable resources. For instance, diesel power plants, oil-based power plants, gas-based power plants. Energy storage, that means utility-based energy storage, like for example pumped storage, like battery storage. Interconnections. The interconnections are extremely important. particularly in the context of a country like India, where we have significant interconnections inside the country, but relatively less interconnections outside the country. We are exporting about 500 megawatts to Nepal, about similar numbers to Bangladesh, and I think we are importing power from Bhutan, but those interconnections are not very strong interconnections. And finally, demand side response, and that demand side response is very, very expensive. If you talk about load side demand response, that is very expensive. Now the three figures on the right here, these are some visualization of the flexible resources in three different countries.
Multiple choice answer আমাকে একটু পাঠিয়ে দিন না।
So you have the flexibility, the flexible resources that are listed here are the interconnections, the hydro,
multiple choice স্যার একটু
pump storage
with answer পরীক্ষা নিতে হবে। হ্যাঁ পাঁচটা চারটে নয় 5-6টা পাঠিয়ে দিন, 6টা পাঠিয়ে দিলে খুব ভালো হয়। হ্যাঁ 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 ঠিক স্যার একটু সম্ভব হলে দুপুরবেলার মধ্যে হলে খুব ভালো হয়।
Okay, so pump storage and hydro, and then you have the interconnections, then the combined cycle gas turbines, and the combined heat and power plants. So these are the resources, flexible resources that can enable the integration of renewables. So for example, the one on the top has some significant amounts of hydro and CCGT. So the pink curve shows a installed wind potential, wind turbine potential of 47%, and these are all installed capacities. So that is for a country, for Portugal. So in Portugal, the flexibility would come from the hydro and the combined cycle gas turbines. In Germany, the flexibility would come from the interconnections. So the plot downwards to the left is for Germany, and to the right is for Ireland. So in Ireland, the flexibility is supposed to come from gas turbines. In Germany, it is supposed to come from interconnections. So like this, every country's grid has to be analyzed, and a similar kind of analysis, if done for, I can't. Okay, so there seems to be some problem because of which this is not visible here. Okay. Let me see. Yeah. So in India, this is the flexibility chart for India on the right. So if you look at the interconnection, it is about 15%, 16%. In India, coal thermal is expected to be the flexible resource. So when I talk about flexible resource, I mean that when the wind is going to ramp down, or when the solar is going to ramp up or ramp down, which resource is going to step in and take up that amount of that generation. So in India, it is expected that the coal thermal, which is fossil fuel based, that is what is expected to be the flexible power reserve. Now this is against all contrary expectations worldwide, where the expectation is that we should ramp down, we should bring down the amount of coal thermal power plants that are existing in our country. However, it is not possible to do so, and it is expected that the existing coal thermal power plants may be made more flexible. So it takes a lot of coal. It takes a lot of coal. Somebody in the POSOCO had once said that it takes a lot of coal to integrate wind. So similarly, in India, we are expected to make sure that our coal thermal power plants should be able to run at extremely low thermal capacity. So for instance, if I have a power plant, a unit of 800 megawatts, it should be able to run at about 450 megawatts. There are problems with this kind of running. So for that, this CEA had actually come out. CA has actually come out with a flexibilization report. And one of the key findings of that report is that the coal-fired power plants in India have to be flexibilized. So what is the meaning of this flexibilization? So the first thing that has been noted here is that in the last 5 years, significant amounts of coal-fired power plants have been set up in the country. Correspondingly, the electricity demand has not risen. Electricity demand has started dropping in many countries in Europe. And the reason is that there is no manufacturing that is going on in those countries. In our country, the electricity demand is still rising, but it is not rising at an adequately fast rate. So we are still having a significant amount of manufacturing going on in the country, and it is expected that manufacturing will increase in future. So it is expected that electricity demand will rise, but the rise is very slow currently. The third thing is that our discoms in India are in very poor financial health. So most of the electricity pricing currently in India is very, very political. People do not want to increase the price of electricity. As a result, the distribution companies are mostly in very poor financial health. So this is the reason why the plant load factor has been monotonically declining over the past 5 years from 77.5% to 60%. And this case is worse for state-run power plants. Centrally owned power plants, the plant load factor is better. So for instance, NTPC power plant has a better plant load factor compared to a power plant that is owned by a private entity like, for example, Adani or Jindal. However, the plant load factor is declining over the past 5 years. So a study was made for the demand prediction in our country, and it was estimated that in 2022 July, 19th of July, it is expected that there will be tremendous amounts of wind blowing. The demand will be very low, and the difference between the peak demand in the day, which is usually in the evening, and the off-peak demand, which is maybe at midnight, maybe at 2 o'clock, 3 o'clock, the demand is very low. That peak is expected, the difference between the two are going to be very, very large. So as a result, in the evening, when the sun sets and the solar drops, the drop in the solar will have to be compensated by increasing the power generation from other flexible resources. And the peak hour ramp rate is expected to be about 247 megawatts per minute. And this is very, very high ramping up. Similarly, in the morning, when the sun rises, all the solar farms are expected to ramp up automatically. As a result, the thermal plants are expected to ramp down. So the sunrise ramp down rate on July 19th is expected to be 368 megawatts per minute. And the reason why this is so high is because the demand is very low on July 19th. This is not summer, it is not winter, it is monsoon. So nobody has switched on their air conditioners and nobody has switched on their heaters. Currently, in our thermal power plants, the minimum thermal load at which the plants can operate is roughly about 50%. What happens if you bring it lower to 50%? There is a problem of flame. The flame stability in the boiler is lost. So the flame goes off, number one. Number two, your main boiler feed pump starts to vibrate at such low rates of water. So this 50%, this number, MTL, a minimum thermal load, must be brought down to about 20 to 40%. So in order to accommodate the renewable energy. So when the wind will blow very fast, the thermal power stations should not be switched off. but they should continue to run, but at extremely low loads. So this is called flexibilization of coal-fired plants. And this flexibilization is a term has been suggested as a way to prepare for huge amounts of renewable energy integration into the grid in the next 2 to 3 years. So NTPC has already started working on this. There is a lot of experience that can be obtained from coal-fired power plants in Germany, in Netherlands, which are currently, for instance, in Germany, some units of about 800 megawatts can run safely at 90 megawatts, which means about almost like 10% is the minimum thermal load. And not just, this is not a temporary phenomenon, they should be able to run at minimum thermal load for several hours in a day. The problem is that you can run the existing power plants in our country at such levels, but then the cost is hidden and you don't know that the life of that turbine, the life of the boiler is actually getting lost. So we do not currently have the technology to measure the loss of life as a result of such low operational operations, so such low levels of operation. We need to come up with some sort of a frequency response, and that is actually going on. POSOCO is looking at ways to increase AGC, the number of units that can be put on AGC, automatic generation control, so that the network frequency is supported in the event of a sudden drop or rise from the wind or the solar farms. So one of the ways that this could be done is using energy storage. Sorry. Using energy storage. So in energy storage, you have utility scale batteries. So these utility scale batteries are currently being experimented in India, but in US and in Europe, there have been some pilot projects where they have installed up to 500 megawatts of battery storage at a particular single location. Similarly, you could deload the wind turbines. Deloading the wind turbine means that if you are having a wind turbine that is maybe it is a 5 megawatt wind turbine. So 5 megawatt wind turbine is running at, let's say the wind speed at that time is 12 meters per second. So at 12 meters per second, the 5 megawatt wind turbine may be generating about, let's say 5 megawatts, because that is the rated wind speed for that particular wind turbine. So deloading means that the blades of the wind turbine are pitched away from the wind, thereby wasting some of the wind purposefully. So the output of that wind turbine drops from 5 megawatts to maybe 4.5 megawatts, thereby creating a reserve of 500 kilowatts. So therefore you have a 10% reserve. And this pitching of the blades is with the help of servo motors, which are located in the hub of the wind turbine. And these servo motors are controlled by a separate controller, which is the pitch angle controller. The pitching of the turbine blades is a slow process. However, it has been commercially deployed in many wind farms all over the world, the controller for pitching in and pitching out of the wind. So this way you create a reserve, and thereby whenever the network frequency dips or the network frequency rises, you could support the network frequency by pitching into the wind or pitching out of the wind, and thereby increasing or decreasing the power output of the wind turbine. Similarly, you could do the same with solar farms. So in solar photovoltaic arrays, you have something known as maximum power point tracking, wherein you try to operate always at a certain voltage so that the current that is drawn leads to maximum power extraction from the photovoltaic array at a certain solar insolation level. Instead, if you reduce the voltage, the same amount of current flows, but the amount of power that you get from that photovoltaic array would reduce, even though the solar insolation is the same. So this is called deloading of the solar photovoltaic array. And whenever, again, when the network frequency dips or rises and there is a need to inject more or less power, you could change the voltage using a DC-DC converter.
Professor, it's not audible, sir.
There may be some network issue.
Okay, can you hear me?
Yes, yes.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. Okay, because I keep getting this message, bad network quality, your network is of poor quality, so I don't know what is going on. Okay, great. So virtual inertia is when you have the power output of the wind turbine or the solar farm change as a result of the change in the network frequency. So deloading of the wind turbines and the solar photovoltaic arrays can give some virtual inertia, and this virtual inertia mimics the behavior of turbines, which are actually shafts, solid mechanical devices which are rotating at very high speed in the synchronous generators, the alternators, and they are locked to the grid frequency. So that is the physical inertia that is available, and this physical and we'll talk about that in a minute, in more detail in a minute. So recently, in fact, in just a couple of days ago, there was a news report. I don't know if you have followed that or not. There was an announcement from the government that all um, old thermal power plants will be retired. There is a proposal to do so, and in fact the ones that are polluting, they will be retired, and there is a schedule that has been declared by the government that these many thermal power plants are going to be retired in the next 10 years. So such kind of non-viable power plants may be converted to synchronous condensers. So till recently, utilities were reluctant to consider the option of synchronous condensers, thinking that it is just a expensive white elephant. There is no need for such kind of devices when capacitors can easily be used to inject reactive power. So in India, there are hardly any synchronous condensers. Very few synchronous condensers are there in India. Worldwide also, there is a reluctance to consider this option. But today, when you talk about renewable energy integration, you talk about system strength and you talk about system inertia. System strength is referring to the amount of short circuit capacity at a particular bus when there is a fault at that bus. So you want that the system strength should be very high, which means that the short circuit level at that bus should be very high, which means that the Thevenin's equivalent impedance at that bus will be very low. So system strength and system inertia can be increased by the condensers. The capacitors cannot do that. Similarly, the STATCOMs and SVCs cannot do that. So therefore, non-viable power plants may be converted to synchronous condensers. Okay, so what is the impact of renewable energy fluctuations in the grid? So when you talk about renewable wind turbine, let's just talk about a wind turbine. And when the wind speed changes, the power output of the wind turbine also changes. But the change, it comes after a certain time delay. So the wind turbine can be represented as a first order delay block. This is the gross aggregate dynamics of the wind turbine. If you, from a control point of view, if the input is a single input, single output system, the input being the wind speed deviation and the output being the power output deviation, then the input and the output are related by a first order transfer function block. The first order transfer function block has a certain cutoff. So the figure on the left shows the cutoff frequencies depending on the weight of the turbine, or the rather also at high wind speeds the cutoff frequency increases. So you have different graphs at 10 meters per second and at 8 meters per second for different inertia, 2.5 seconds and 10 seconds. So inertia h equal to 2.5 seconds means that it takes 2.5 seconds to accelerate that particular shaft from zero speed to its synchronous speed. So inertia of 10 seconds means that it is a very heavy shaft, and inertia of 2.5 seconds means it's a very light shaft. So at low wind speed and at low inertia, you can see that the cutoff frequency is higher because the shaft inertia is very low. But if the shaft inertia is very high, the cutoff frequency is lower. Similarly, if you have a low voltage situation arising at the point of common connection, point of common coupling, so you have a wind farm connected to the grid, and because of some disturbance in the grid voltage drops. How does the wind farm respond? How does the wind turbine respond? So here we are talking about a doubly fed induction generator, which is the generator that is usually connected to the wind turbine at high power level. So a typical 5 megawatt wind turbine would generally be connected to a doubly fed induction generator. Smaller size turbines are connected to fixed speed generators. The benefit of using a doubly fed induction generator is that it allows you to operate at different speeds. Thereby you can actually extract more and more power from the varying wind speeds. So the problem with doubly fed induction generator is that when the terminal voltage of the generator drops, the rotor current rises. And here you can see in the bottom figure that the rotor current rises by at least 4 times. And this can easily destroy your rotor side converter. So of course, this kind of situation forces you to actually switch off the wind turbine in the event of a low voltage situation in the grid. So such an action can become very costly. So the grid actually comes out with different grid codes, and in India also we have a similar kind of a grid code that mandates that if you want to connect to the grid, you need to be able to remain connected even if there is a temporary under voltage situation or an over voltage situation. So therefore you need to take action inside your generator to protect itself without disconnecting, so that it is able to inject active or reactive power into the grid when during the voltage sag. So some countries, like for instance in UK, in Germany, they mandate that a DFIG must inject reactive power into the network when there is a voltage sag. In India, in Ireland, Irish grid code, Indian grid code, they mandate that some wind turbines should actually continue to inject active power even when the voltage is voltage quality is poor. So this different kinds of grid codes mandate different kinds of behavior, expect different kinds of behavior from the wind turbines. So here we have the dotted curve on the left, the red dotted curve shows the active power variations because of wind speed variations. The wind speed variations are shown in blue. And the same variations applied, the same changes applied at 10 meters per second and at 12 meters per second are shown below. And you can see that the same change applied at 10 meters per second causes a much lower change in the power output compared to if you apply the same change at 12 meters per second, the power output changes by a much faster. So which means that if the wind is blowing at very high speed, and at that very high speed the wind fluctuates, then the impact on the grid is much more compared to if the wind is blowing at very low speed, ambient wind speed is low, but the fluctuations are the same. This is a matter of concern. Also, the this graph on the right shows what happens if you have a 92 kilowatt load rise. So at 5 meters, at 5 seconds, the load increases in a small microgrid. A load has increased by 92 kilowatts. And at 25 seconds, the wind has dropped. And that drop in the wind causes a similar 92 kilowatt change in the generation. So basically, the same kind of event has occurred, which is that the generation load mismatch of 92 kilowatts has occurred at 5 meters per second, at 5 seconds and at 25 seconds. The first event is more severe because it is a load change event. The second event is much less severe because the wind inertia is actually, the shaft inertia is actually reducing the hammering effect of the event. And the three graphs here, A, B, C, refer to different wind penetrations as well as the availability of spinning reserves. And you can see that when the wind penetration is higher, the frequency nadir, which is the lowest point in the frequency because of the event change, the frequency nadir is much lower and it is more severe, the frequency change event. And if the wind penetration is low and the spinning reserves are also present, which is the curve C. Spinning reserve means that you have some other flexible resource that I was just talking about. That flexible resource immediately steps in to compensate for the change in the wind generation. So if such a situation occurs, then the frequency change is further mitigated, as curve C shows on the right. That is the frequency. When we talk about the frequency for a change because of an event, the inertia affects the rate of change of frequency, which is also referred to as rock-off. So if you have a low inertia power system, the frequency changes at a very high rate, so the rock-off is very high. Similarly, the nadir, which is the lowest point in the frequency, also becomes much more pronounced when the inertia is low. So how can we improve the situation? We can actually improve it by introducing more and more ambient more and more virtual inertia. Now, there is another kind of frequency study that we at IIT Delhi are also doing. So there is a recent paper actually that is available in IEEE on transactions and power system by a group from MIT, which talks about ambient frequency. How is the ambient frequency changing? How is the ambient frequency affected because of the inertia? So here we have observed that the role of inertia is very less pronounced, relatively unaffected. It does not affect the ambient frequency. It only affects the frequency distribution when there's a big load change. Then what affects the ambient frequency? So this is a probability distribution. So it's basically a histogram plot of the ambient frequency collected over 24 hours. And here it is shown that it shows a bimodal distribution. Now the bimodal distribution is not always seen. So for instance, if you do this study on the Indian grid, you do not see a bimodal distribution. But here, for example, this particular graph is coming from the UK grid. It shows a bimodal distribution indicating that there is a frequency corrective action. And that sort of makes the frequency stay in the range of 50 Hertz, or in this case, delta frequency to remain in the range of 0 Hertz or 0 millihertz. The frequency corrective action has a certain deadband associated with it. So the governor, which is the installed in the steam turbines, has a certain deadband, which is shown in bottom below in the left. This deadband says that, say here for instance, a deadband of 15 millihertz indicates that if your frequency deviation is within plus minus 15 millihertz, then the governor will not respond. So on the right, you can see that if the deadband size is increased, the frequency deviations will increase. And if the deadband is made tighter, the frequency deviations become more and more clustered around zero. This is a very interesting finding here, and we are trying to establish the same in India. The only problem is that in India we do not have such a regulated frequency all the time. However, we have been able to observe some similar characteristics in the frequency, ambient frequency distribution in Indian grid also. Similarly, there is something called load reversal time. So if you look at the general load on the power grid, I'm not talking about the load at a particular bus, but I'm talking about the amount of load that is there in the entire grid. So you just sum up the entire load of the system. How do you do that? So the entire load of the system cannot be actually measured. What can be measured is the amount of generation. So, in the mess, how many rotis are eaten by everybody cannot be measured. However, how many rotis are being cooked in the kitchen can be measured. So the load is estimated by actually the generation. So here, when you look at the load for the power system, so every system has a certain load reversal time, which means that the load shows gradual variations, and this load reversal time is generally about 30 seconds to 1 minute, maybe 5 minutes. So in industrialized societies, the load is very, very steady because of the high level of industrial load. While in a society like ours, where the load is primarily agricultural and domestic load, the load fluctuates very fast. So the load reversal time is much less. So here this kind of a study was done for different load reversal times, and it is seen that the load reversal time has significant impact on the PDF of the ambient frequency. So what can be done? Well, energy storage and enhanced primary frequency response is the only way to improve the spread of the ambient frequency around the 0 hertz or around the nominal frequency. So we looked at IIT Delhi, we looked at the something known as dynamic locational grid flexibility. So here what we have done is we have looked at how does the grid vibrate when it is being hammered by a renewable energy resource. So if the wind is fluctuating and the wind farm is connected at a particular node, the entire system is basically being hammered from that particular node, and the system then vibrates. Those vibrations are measured, and those vibrations are actually observed using some linearized systems, linearized models of the power system. So if a certain node has the ability to make the power system vibrate at a faster rate, then we say that that particular node is having reduced inertia. Similarly, if you have a wind farm connected at a certain node and that wind farm's output changes by a certain amount, say the wind farm output has increased. Now this increase in the wind farm output moves the system to a new operating condition. This new operating condition is closer to instability. Then that particular node has the ability to move the entire system closer or farther away from instability. So that particular node is considered to be a very vulnerable node. On the other hand, you may have another system on which a wind farm, the renewable energy fluctuations do not result in any impact on the system. This means that such a node has extremely high inertia. Similarly, if you have some change in the operating condition at a particular node, it has no impact on the system's dynamic characteristics, like for instance, the damping and the frequency of the principal modes of oscillation. So here let us talk about a seesaw. And a seesaw, two kids are sitting on the two ends of the seesaw, and the seesaw is going up and down. So if the weight of the kid is changing, it will result in the seesaw going up or down. So that means that location where the child is sitting is an extremely vulnerable location. But if the child sits in the middle of the seesaw where the fulcrum is located, then even if the child's weight changes, it has no impact on the movement of the seesaw. So such a location is called a center of inertia of the system. So therefore we have defined two indices. One index is called the flexibility index and the other index is called the inertial index. How do we define these indices? We define this based on the small signal stability analysis of the power system. So small signal stability analysis means it is these indices can describe the behavior only when there are very, very small disturbances in the system. So for this we need to linearize the system because our power system is mostly nonlinear. So once we linearize the system, we can calculate the eigenvalues. And once we calculate the eigenvalues, they are the principal modes of operation, principal modes of oscillation. Then we look at how many generators participate in these modes of oscillation. And based on that, we calculate which mode is widely distributed and which mode is extremely localized. The extremely localized mode of oscillation is called a local mode of oscillation, and the extremely distributed mode of oscillation is called an inter-area mode of oscillation. Now, depending on the kind of mode that it is, the stability property of that mode also comes out from this analysis. So an inter-area mode of oscillation is usually more critical compared to a localized mode of operation, which means that if all the generators in the system are participating in a particular mode, then that mode is usually the most dominant and critical mode. So corresponding to such inter-area modes of oscillation, we identify the dynamic behavior of the generators, and we observe that the generators behave in groups. These groups are called coherent groups because the generators in a coherent group have very similar dynamic properties. Their oscillations are usually in phase, and you will have 2 or 3 groups oscillating against each other. So using these coherent groups, we define the sensitivity of the eigenvalue to the load change on a particular bus, and based on that some equations are there. Using those equations derive naturally from the linear algebra, techniques of linear algebra applied to the state matrix, the plant matrix, the A matrix of the system. Based on that, we define two indices. One is the flexibility index and the other is the inertial index. The inertial index is an indicator of how the total system inertia is spatially distributed across the system. So this kind of spatial distribution tells us that if you have a bus where a large inertia is present, that bus is the center of inertia of the system. So for instance, in this particular system, bus number 1 is the center of inertia. Bus number 1 and 9 is the center of inertia. So here, if you have a fluctuation, if you have some hammering going on at bus number 9 or bus number 1, the system would not even oscillate. There would be no impact on the system. Similarly, we define the I'm sorry, just one moment, please. Sorry about that. So this kind of an oscillations which are obtained from oscillation analysis, which is obtained from the linearized model, can be verified very easily using nonlinear models as shown here. The nonlinear model here confirms that bus number 1 and bus number 9 oscillations are very low. You can see that, while bus number 19 and bus number 20 oscillations are very high. So bus number 19 and bus number 20 here, you can see bus number 19 and bus number 20 are very, very vulnerable buses. Bus number 9 and bus number 1 are the center of inertia of the system. Similarly, the flexibility index shows that the most flexible bus would be the bus where if you change the load or if you change the generation. Why is the generation changing? Because suddenly you have cloud movement over the solar farm, suddenly the wind drops. As a result, the system moves to a different operating condition. However, if this kind of an event occurs on bus 14, which is the most flexible bus of the system, then the operating stability of the system is unaffected. So using this flexibility index and the inertial index, we have also analyzed the stability of the system, and we find that the inter-area power flow, changes in the inter-area power flow actually results in buses moving closer to the center of inertia or moving farther away from the center of inertia. So this way we can define some critical tie lines, inter-area tie lines, and these tie line power flows can change the spatial inertia in real time in the system. Remember, the physical inertia is located in the same place, it does not change. However, the distribution of that inertia across the entire network is affected by the power flows on critical tie lines. Not all tie lines, but the critical tie lines. These tie lines are the tie lines that are connecting coherent groups of generators. So we did this analysis for a large system, in our case the northern grid of India, and we find, so this is a description of the work that was done on the northern grid. Of course, the data that was used is old data, it is not recent data. So the results that you see right now are not applicable to the current situation in the northern grid. It's actually 1960s data. So the northern grid, on the on the left hand side you see the map of India, particularly the northern grid, and we divided all the generators. We had about 240 generators in the system, and those 240 generators are divided into 7 groups, each group behaving in a similar fashion. The line diagram on the right corresponds to the geographical location on the left. And here you can see that the center of inertia has been identified to lie in eastern UP. That makes sense, because there is a lot of generation out there, Singrauli, Rihand, and I think Tanda and all those things. NTPC plants are all there located. So the center of inertia, so that's a very heavy generation. The ones in the north, you have a lot of hydro generation. So the northern grid has a typical characteristic that a lot of thermal generation is located in the eastern UP, southern UP, and a lot of hydro generation is located in Punjab and J&K. Uri is there, Bhakra and all those things are there. And on the left, in Rajasthan, that is the vulnerable region, and we find that that region is the least flexible region, which means that if there is a change in the operating condition in that region, the entire system is affected. It may become more stable or it may become less stable. However, in the middle, there is a legend there, it says flexible region. So right there, which is western UP, that is a very flexible region. So there, if you have a lot of fluctuations in the wind farm output or the solar output, then the system's stability margins are not affected, and the system is relatively unaffected by fluctuations happening there. So how does this help us? So obviously one of the takeaway points from this discussion is that we should locate our fluctuating resources in the most flexible region. We should locate any resources that has the capacity to hammer the system. We should locate them in the center of inertia region. However, that is not possible obviously, because you will locate the wind farm only in that location where wind is blowing. So maybe it is not possible to locate a solar farm in the flexible region because there is no sunlight there. So therefore, the next step is to plan for the integration of energy storage. So this study actually helps us to determine how much money we should spend on energy storage. So we find that the global stability condition, the global stability can be restored through a local control action. So if you look at the top left hand graph, what we have done is we have located a renewable energy system, siting, it is not sitting, okay, sitting maybe siting, I don't know whether there's a double T or a single T in siting. But anyways, so it is located at bus 174 of group 1. So group 1, I don't know if the groups are mentioned here. Group 1 is in the middle there, you can see the group 1 is in red. So if you locate the renewable energy in group 1 and the control action, so you see here the lower axis, the x-axis shows what are the different kinds of control actions that you can take. So 1, 2, 5, 3, 4, 6, 7, 8. So 1 corresponds to injection reduces to 50 megawatts. You can see the legend bottom right hand. 2 corresponds to load shedding in group 1. 3 corresponds to load shedding in group 2. 4 corresponds to load shedding in group 4. Sorry, group 3. 5 corresponds to load shedding in group 4, like that, okay? So if I reduce the injection by 50 megawatts in group 1, which is the top left hand graph, the damping of the most critical mode reduces. To restore the damping back to its original value, I need to take control action number 2, which is load shedding at group 1. So that means if I do the load shedding in the same group where the injection has been reduced, then the damping is restored back to 0. Similarly, if you look at the graph for group 3, for instance, in group 3, the green graph, the green dot corresponds to control action number 4, which is load shedding in group 3. Similarly, if you look at the renewable energy siting for group 4, the control action that will restore the damping back to 0 is corresponding to control action number 5, which is basically load shedding at group 4. So here what we are saying is that if the renewable energy fluctuations are mitigated using energy storage located within the same group, then the global stability of the large grid can be restored back to its original condition. This is a very important finding. The another research that we are doing here at IIT Delhi is how we can look at the uncertainty that is introduced into the system because of renewable energy fluctuations. To understand this, we need to understand how does a deterministic system, which is what the power system is. A deterministic system is a system which is described by very clear differential equations. These differential equations are usually ordinary differential equations, which means that the independent variable is always time, and the dependent variables may be, the phase angle, the rotor speed, the voltage, the flux, and things like that. So such a deterministic system, when it is modulated, when it is hammered by a random input, that random input has a certain statistical property. What is that random input actually? It is the fluctuations emanating from a renewable energy system. So such a random input when hammering a deterministic system, the output of such a deterministic system, so this is a very simple system, it's like a seesaw system, single input, single output system. The output in this case would be the frequency. How does the frequency reflect the statistical property of the random input? To understand that, we need to measure the frequency. So that frequency is measured very easily. That is fine. But then that frequency that has been measured is the output of a deterministic system. So to extract the statistical property out of that, we cannot generally straight away analyze that time series signal. We need to make sure that every sample within the time series is independent. There is no time correlation between two successive samples, which means that we need to downsample. Only downsampling will allow us to reclaim the statistical property of the input, thereby completely removing the determinism out of it. If we do so, then we will find that the output of the deterministic system depends only on the input and not on the deterministic system. This means that if the input statistical property changes, that change will be accurately reflected on such a processed frequency measurement. So we are actually, that means we are actually able to determine how much renewable is currently injecting into the grid, how much randomness is being currently injected into the grid. And that randomness is coming from the renewable, that randomness may be coming from the load. Then we can distribute, we can discriminate between the randomness of the load and the randomness of the renewable. And we can say, okay, right now we have the randomness of the grid is 100. Out of that, 60 is coming from the renewable energy, 40 is coming from the load. At night, 70 is coming from the load and 30 is coming from the renewable energy. If you remember, on 5th of April 2020, there was a light off event in India. All the lights were switched off and the loads just dropped. There was a huge drop in the load. So at that time, how does the randomness of the frequency measurement change? So then we find that the randomness could accurately say, that the randomness in the grid is completely dependent only on the renewable injection and not on the load injection at that time. So this is work in progress. I do not have any results to show from this particular study at the moment, but we are very excited about whatever small results that we have got till now. And perhaps in a future date, we could discuss more about this study here. So I have come to the end of my presentation. So is there any, so I would now like to welcome any questions that you may have. How are we doing for time? I don't know. Any questions or feedback or any comments, I would welcome.
Doctor, good.
Yes, yes, please.
Yeah, good morning.
Good morning.
Yeah, the point is that uncertainties. So at uncertainties, you are taking the non-uncertainties or you are taking unknown uncertainties. When unknown uncertainties are there, what will be the consequence? When non-uncertainties are there, what will be the performance? How much will be the steady state error? You got my question, please? Can you hear me?
Yes, you are audible. So within short period, sir will clear your doubt.
Okay, fine, fine.
Sir, as per your suggestion, which energy is more stable out of all these?
Oh, can you hear me?
Yes, sir. Yes, sir.
So
Yes, yes.
I got disconnected somehow. The network, there are some network issues. I'm very sorry. Somebody was asking a
Yeah,
question.
absolutely.
Can you please
Yes, yes, sir.
just can you please
Uh,
start again? Yeah.
Out of all these energies source, which one is the perfect, matlab, stable? Suppose thermal, renewable, hydel, and apart from all this.
Uh, um, which source out of all these sources is stable?
Yeah, yeah, yeah,
Stable as in, so when we talk about stability,
yeah.
it has a lot of connotations. So what
Okay.
kind of stability are you asking for?
That is suppose thermal, suppose some blackout, some island, so many issues coming in thermal. Likewise, hydel. So some pros and cons are there, but overall, in research,
So
what are the papers?
there is no easy answer to your question, of course, because these are very complicated issues. There's a cost of economics also involved with this. You also have to see what resource is available to you. So thermal energy technology has matured over the past 100 years, and it is dispatchable. It is very much controllable, and our grid has developed, evolved, taking into account thermal energy systems, thermal power plants. Wind power plants are not polluting. It is relatively new technology. In terms of stability, electrical stability can be controlled using controllers. Mechanical stability requires a different kind of controllers. So it's a difficult question to answer very in short. So there are aspects that are good and bad about all kinds of generation technologies.
Okay, sir. Thank you. Thank you.
Thank you.
Yeah, yeah. Good afternoon. I asked the question.
Please. Sorry, I lost you actually. I got disconnected. Please repeat your question.
Oh, that's all right. No problem. Question yeah, I have two questions. One question is this:
Yeah.
when the uncertainties are known and when uncertainties are unknown, at that point of time, what will be the performance and what will be the steady state error in both the cases?
Are you talking about, are you asking in the context of the latest work that I presented, or you're talking in terms of a general question?
That is uncertainties.
So I will try
You
to
have
answer your question
incorporated the
from the latest
uncertainty.
work that we are talking about. So
Okay, fine. Yes, please go ahead.
তুলে রেখে দিও।
Hello, hello. Can
Yes,
you hear me?
please go ahead.
Yeah. So
Yes.
the uncertainty is generally analyzed using something known as stochastic differential equations. So you have ordinary differential equations where everything is very deterministic. So all the parameters are well known ahead in advance. So such a system is well defined and the uncertainty is zero in such a system. To analyze the uncertainty of renewable energy systems, we need to go for something known as stochastic differential equation. So the wind speed, if you just measure the wind speed and try to model the uncertainty that is there in the wind speed, that it follows a typical distribution which is known as the Weibull distribution. So a Weibull distribution, of course, some locations may follow Weibull distribution very clearly. Some locations may not follow a Weibull distribution. So every location has a typical peculiarity, but that there are very advanced statistical techniques today which can actually model the probability distribution of the wind speed. As a result, that probability distribution, once you have modeled it, you set up basically a system of stochastic differential equation in which your variables, the random inputs are injected. These random inputs belong to a family of probability distribution function that you have just now estimated. And the output of such a system of differential equation is then analyzed again using the similar technique to find out how much of the input statistical randomness is reflecting in the output. So this is what we are doing in this particular study, where we are trying to estimate the randomness of the input from the randomness of the output, assuming that the randomness of the input is not measurable, but the randomness of the output is measurable.
So any other?
Okay, another question. Yeah, another
Yes.
question
Yes.
that you have stated in one of the place in during your presentation that government is planning around 40% of the thermal plants as a isolation. So what will be the, you can say, because the exponentially demanding of the power, so how it will be that is accomplished to fulfill the demand in the future, and this renewable that may not be enough to accomplish the demand. So what will be the alternate another sources, whatever the thermal plants are being maybe isolated, maybe the discarded, maybe the stopped? So that is my related question.
So yeah, it is a very interesting question, and again, once again, I do not have an answer to that actually. So it is a ongoing analysis.
Okay, no problem, no problem. Because you are working, so you are related more deeply on that. That's what I share the question.
So it is actually
no problem.
It is actually a question of resource planning. So this kind of question will be better answered by somebody who's working in the, like for example, CEA. The CEA has brought out a lot of reports on that. Central Electricity Authority on resource planning. So I think your answer is lying in those reports.
Thank you. So nice of you. Have a nice time.
Thank you for your question. Yeah, thank you.
Dr. Biman, Dr. Aniruddha, Dr. Bhore. So would you like to say something? Bhore, Biman, Aniruddha.
Good afternoon, sir. Aniruddha here.
How are you?
Yes.
Doctor?
Yes, sir. I'm fine, sir. How are you, sir?
I'm fine. Thank you.
Excellent lecture as usual, sir. From you, we have received a very interesting lecture, and I think participants are very much benefited out of this.
Okay, thank you very much. Thank you for your patience and your questions.
Yes.
So I think we will conclude here, Dr. Bhaumik.
Okay, so thank you, sir, for your nice and informative presentation. So we look forward to having you again in our next series. Thank you once again from the part of participants, NIT Durgapur, and as well as AICT Auto Training and Learning Program. So
thank you very much.
Okay, sir. Thank you, sir.
And if you have any questions or any other discussions, please feel free to contact me at my email address, which I have. I'm putting in the text box.
Okay, right, sir.
Okay, sure.
Thank you, sir.
Thank you very much.